So in this video, we will be discussing something called convoy effect. Alright. In the last video, we have already discussed what first come first serve is. Okay. So there is a downside of this first come first serve algorithm, and what is that? That is called this convoy effect. So let's take an example. Let's say this is a highway, okay, and there is a service road. Alright. So four cars are moving towards this highway using this service road. Okay. So what happens is, in this highway there are no obstacles. So all these four cars are moving very fast. But let's say the moment these four cars are getting into this highway, what happens is they see there is a big convoy going on. There is a VIP. There is a big convoy of this VIP going on. What will happen? All of them will be slowed down. Okay, their wait time will be much more higher than what their wait time was in this service road. All right. So as a result, what happened? Due to this VIP, due to this convoy of this VIP, they ended up with higher wait time. Okay. So in fast come fast serve also, sometime we may end up in such situations. Okay. So this is called convoy effect. Now let's see with some examples. Let's say there are three processes. Process 1 arrives at time t equal to 0 with much more higher burst time, that is 100. Then process P2 arrives at time t equal to 1. Similarly, process P3 arrives at time t equal to 1. But both of them are having very small burst time, that is 1 and 1. So now let's fill this table and let's make a Gantt chart also. Okay. So let's say this Gantt chart is starting from time t equal to 0. Alright. At time t equal to 0, this process 1 has arrived. Alright. Process 1 is scheduled. So this is non-preemptive schedule. So when this process 1 will be completed at time t equal to 100. Alright. By the time you reach time 100, you have process P2 and process P3 both. Okay. So, okay, let me correct it. So both of these two processes are having same arrival time. So what will happen? Now which process will be chosen? This process with lower process ID will be chosen. So let's say this is process 2, and process 2 will be finished at time t equal to 101. Then process 3 will be scheduled, will be finished at time t equal to how much? 103. Alright. Now let's complete this table. Okay. So when this process P1 is getting completed at 100, when this process P2 is getting completed at 101, when this process P3 is getting completed at 102. Alright. Turnaround time is completion time minus arrival time. Okay, let me change the color. Completion time minus arrival time. So what happens is, this is 100, this is 100, this is 101. Okay. So now wait time is, do you remember, turnaround time equal to burst time plus wait time. So wait time is turnaround time minus burst time. So if I reduce, subtract this burst time from turnaround time, we will be getting this wait time. So wait time is 0, this wait time is 99, this wait time is 100. So response time. Now let's see the response time. So when this process P1 has arrived at time t equal to 0, when this process P1 is scheduled for the first time, that is also time t equal to 0. Alright. So response time is this gap between this 0 and this 0. Okay. Now process P2 arrived at time t equal to 1, scheduled at time t equal to 100. Alright. So what is the gap? 100 minus 1, that is 99. Now process P3, when it is scheduled at time t equal to 101. Alright. When P2 has, sorry, when P3 has arrived at time t equal to 1, so 101 minus 1, that will be how much? 100. Okay. So if you see this wait time of process P2 and process P3 has significantly increased. Alright. Not only wait time, turnaround time, your response time, everything has significantly increased. Alright. So if you see this average response time, average waiting time, or average turnaround time, all of them is much higher here. Okay. Due to this convoy effect. Alright. So the next thing is, let's say if there is a high burst time process that is arriving early, all other processes will end up waiting for more time. Okay. So all of these following processes will be waiting for much more longer time. Alright. This is what we have seen using this example as well. So now the next question is, how do you prepare the Gantt chart for this first come first serve algorithm? So whenever you are at time t equal to k, let's say you are at a time that is time t equal to k. Now see all the processes with arrival time lesser than equal to k. So that means all those processes have already arrived by the time you have reached time t equal to k. Now remove all scheduled processes. Why? Because those processes are already scheduled. Why to schedule them again? Okay. Now remove all those scheduled processes. Now you will end up with all the available processes that are ready to be scheduled. Alright. Fine. CPU may sit idle if no process is there. Alright. Fine. As expected. So what is the data structure we are looking for here? That is a queue that we have already seen in the last video where I have discussed on the first come first serve. All right. So for whatever example we have seen, so nowhere we have seen this context switch time. Okay. So as we all know, this context switch takes a lot of time. All right. Because whatever process is currently running, all right, that context has to be saved and that process has to be pulled back from CPU. New process has to be assigned with its saved context. All right. So there is a quite heavy task going on, even though dispatcher takes care of those things, but it takes some time. All right. In one of the future videos, I will be adding some context switch time. Okay. So then you will be able to understand how you can make this Gantt chart, all right, and how you can fill this table given that you have some context switch time. All right.